Okay, I'm doing a simulation on Fallstat. This is actually from a circuit I had on a different YouTube channel that I put out there over a year ago. And the idea is, because we know series resonant circuits produce or can produce high voltages, if the Q's high enough and all that stuff. Well, over a year ago I was investigating, okay, exactly why do you get high voltages? Exactly why? And I noticed it had a lot to do with the current and the impedance, flowing through that series resonant circuit. So, at the frequency you're running it at, etc. But anyway, I kind of started wondering, well, okay, if you took a series resonant circuit and at the exact right period of time you short circuited the ends of it, well, wouldn't that form a tank circuit, but yet it's generating high voltages? And it's got all that energy still circulating in it, well, what would happen? So I started investigating further, and the on Fallstat, I was playing with it because back then I didn't have the equipment I needed to really do tests on it for real. But my equipment's all fire damaged and got a jittery function generator, and anyway, but the fact of the matter is that it predicts that you're going to get a high voltage, higher than what you apply. Now here I got a 10 volt source, right? Because this is based on my original circuit, and we'll get to the results as we go on this. And I got 212 ohms in there to limit the current to about 47 milliamps when I close this switch. And so you leave it closed until that inductor charges up. So you're charging it with a DC current, and then once it's fully charged, you open that up, all right, and that energy that's stored in the inductor has to go somewhere, and I have it going to an undersized capacitor here. So you take this energy and apply it to this capacitor, it's going to generate a higher voltage than you're applying to it. Now right here, this thing's predicting, based on this, and maybe I should try, actually setting it to the same parameters. In fact, I guess I can try that real quick. But see, the problem is I got I got my power supply in constant current mode to do this. So this is just the most convenient thing. But at any rate, it's predicting, that, as you can see down here, that, for 10 volt output, I'm getting a peak of about 12 volts, and that's about 24 volts peak to peak, right? And so here is the circuit that I actually threw together, for real. I mean, here's your 100 nanofarad cap. This choke's about 7.2 pico or millihenries, and I got a 100 ohm resistor that I'm hooking to my power supply, which I set at 2 volts, but I got it on constant current mode so that it's limited to 45-ish milliamps. Because I'm just trying to prevent this thing. I don't want to blow out all my equipment because I generate some high voltage or anything with it. So I'm being cautious. And at any rate, that gets down to like 0.6 volts or something like that, under those conditions. And really down to about 0, of course, when it's fully charged. Or, well, not quite 0, but close, because it's dropping some voltage across the resistor there. So you can do the math on it, 45 milliamps or 47-ish, but let's call it 45. It'd be about 4.5 volts in theory, but of course this thing can't go up to 4.5 volts. But anyway, No, I miscalculated. It's not a 100 ohm resistor, it's a 10 ohm resistor that I'm using. So yeah, it'd be about 0.45 volts, and that's about what you see when this thing's, you know, fully charged, you know, when it's got all the, you know, current constantly flowing through it. At any rate, then all of a sudden, you know, I will disconnect it, you know, using the alligator clip, and that's the waveform I get. So, and as you can see, I mean, I got this set to, I'll explain it to you, 2 volts per division on the yellow trace, because that's what we're using. You know, and this is bottoming out at 8 volts, so it's probably 9 or 10 volts peak. But what I'm using here, this choke I have, you know, is a low frequency choke. You can see that it's a laminate core. I guess I could try to zoom in on it. But yeah, it's a laminate core, so it's, you know, it's a low frequency choke. So that means it's going to be really lossy, particularly at about the 5 kilohertz this thing, you know, is trying to generate. All right, but you know, you are, you know, kind of seeing that, and like I said, it's you know, you are kind of seeing that now. The, you know, I'm not getting a frequency reading because I stopped the thing, you know, I got it triggered, but it does, I have certainly seen frequencies like that out of this. But I wanted to make some adjustments, but let me I guess I'll use my little hands thing. And try to get it so you can see it. Okay, hopefully that'll hold there. But so let's try it. Let's try it again. But again, this would have about a 20 volt peak to peak signal, you know, if it were working. At least on that test, it doesn't always seem to work. But let me go ahead and short it and apply it. Okay, so you can see it's in constant current, about 46.46 volts at 0.45 amps, or 45 milliamps rather. Okay, now let's release it. Alright, so this time, you know, I only got a VPP of about 8 volts, but keep in mind at most I'm applying 2 volts to this thing, you know, and we got a frequency of about 10 kilohertz this time. But again, there's a lot of chatter in here, you know, so this is the real resonant frequency. That's a classic tank, damp tank response right there. So, let's see, we're at 50 microseconds per division, so, you know, you can figure 1, 2, 3, 3.5 divisions. I guess I could use cursors. Well, I don't want to screw it up. Still trying to get used to some of these things. But, so 3.5 times 50 microseconds, 0.0005. Okay, it's about 175 microseconds. So it's about 5.7 kilohertz. So, you know, that's about where this Volstat was predicting it would be, despite the lossy core and everything. But anyway, let's go ahead and try it again and see what happens. I get different results, you know, in practice, which you might expect. There we go. Okay, shit, that's, you know, 13 volts peak to peak. I still got it set to the same 2 volts per division, so let me go ahead and reduce that. You know, so that produced, you know, 13 volts. But again, it's more than that because, again, it gets damped so fast on this that, you know, it gets damped so fast that you know, you really aren't getting a good peak-to-peak reading. But let me do it again. Okay, this time we only got about 9.7 volts, but again, it's going to be, you know, so I got it set to 5 volts per division right now, so it's about 14 volts in practice. Let's try it again. Again, this is a really lossy core. You got to leave it on the full time. Nope, it's even less this time. Unless that was a mistake. Okay, so you know that produced, you know, about 14 volts peak to peak. So again, it's, you know, it's not out of the question, especially for the choke I have and everything like that. It's going to be lossy as hell. That's why I keep getting different results. It just kind of depends on how moody its core is, you know. But like I said, I'm not putting much current through it, you know. Okay, so we're getting pretty consistent results here now. So let's do a test. Wait, let me pause the video for a second. Alright, at any rate, I've carried this through to its logical conclusion, and I put my probes into 10x mode and changed the scope reading, and, you know, I've upped the current to where it's like 200 milliamps max. So, and you can see the kind of voltages we're getting out of it. You know, it's actually about 68 volts peak to peak. And again, remember, this is heavily damped, so it's actually going to be higher than that in practice. This capacitor I've got on here is only a 100 volt capacitor, so I don't want to go any higher than this. But it proves that yes, you can use a parallel tank circuit to generate high voltages. You know, unlike everybody out there thinks, you can do it. So, you know, this is proof. I mean, here I'll run the test again. Say 164, 183. So, you know, I'm running out of voltage before I run out of current. But, pop, you know, 72.27 volts at 4.8 kilohertz. And that's pretty much what FileStat would predict. But let's, you know, it's not going to be exact, because again, this is a high loss core. But let me make some suitable adjustments. I'm going to go ahead and take our resistor down to the same 10 ohms I'm using, and I'm going to set our power source here at 2 volts just like mine is, because again, I wouldn't want to up the volt, because I don't want to have this capacitor blowing up right next to my leg here. So and it might, you know, we're starting to put more and more energy into this inductor. So let's go ahead and run this SOB and see what it does. I don't know if this coil resistance is right either. I never measured it. Okay, so you know, this is actually charging up to a higher voltage than my power supply is, evidently, because this got up to 199 milliamps. You know, so maybe it has a higher resistance or something. But okay, so this is predicting about a 48 volts, so it's about 96 volts peak to peak. But again, this core isn't a high loss core like what I'm using here. So, but again, we're not far from that, and the frequency is, you know, 5.9 kilohertz or so. My frequency is 4.8 kilohertz, but again, it's a lossy core. I'm surprised it oscillates at all, you know, because it's eating energy with, you know, not just with every oscillation, but every time it changes, it's eating energy, and it's a lossy core. So, you know, you got eddy currents and all that in there absorbing it. And again, if I used a, you know, a ferrite inductor, or, you know, you know, like common mode choke or something. This is like a 3 millihenry choke, so, you know, versus a 7 that I've got hooked to it. So, but this would be higher frequency. It probably. But I've got other cores like that, but that's, you know, pretty low inductance. It wasn't quite enough. you know, I mean, I could have just reduced the size of the capacitor, you know, and got the same results with a lower inductance core, got, you know, a similar ratio, you know, and I could have gotten exactly the same results. But this shows that, yeah, I mean, believe it or not, parallel resonant circuits can produce high voltages and potentially dangerous voltages too, because if it's a big enough choke, I mean, or big enough inductor you have, could store quite a bit of energy, you know. So the bigger it gets, now this still isn't storing a lot of energy. It's you know, again, I had it to south of 200 milliamps, right? So it's, you know, zero point 0.2 squared, and so that's about, let's see, divided by 2, and then multiply by our 0.0072 Henry core. You know, it's about 144 microjoules according to this. So not a lot of energy, you know, not a lot of energy at all. So, but still, you know, if you were to carry this up into the ampere range, you know, and really start to put some energy in that. Again, my simulation, and this is what caught my attention, and I'll show you what I originally did on the simulation. And instead of a 10 ohm resistor, I used a 1 ohm resistor. And this isn't going to be the same. Originally, I started with a 10 millihenry coil in the original simulation. But let me go ahead and run that and show you what the results are. Okay, I'm charging the inductor. 1.1 amp, 1.2 amp, 1.3 amp. It would probably be faster if I didn't have 50 milliohms in there. Shit takes a long time. I got this thing set to high resolution, so let me short that thing out. Speed it up a little bit. Let me try to speed this in. Oh, remember I reduced the voltage? I forgot about that. So I had it set to 10 volts originally. So, you know, we're up there to that high current. Now let's open the switch and see what happens. Wow, 2 kilovolts, 2.4 kilovolts. You know, that's based on the 10 amps we stored. It's about half a joule, I calculated. But the problem is this capacitor can't handle half a joule at no low voltage. So it has to, the only way a capacitor can store energy is to have it at a higher voltage. So that's what has to happen here, this interchange between the inductor and the capacitor. You know, because the inductor's got to fully run out of energy before it'll release its voltage. Then its voltage goes to 0 the moment it runs out of energy. Until then, it's going to generate whatever voltage it can, as long as it's still got energy stored in it, to get rid of it. Whatever it takes. You know, it's trying to maintain current flow. The capacitor can only just absorb that. That's all it can do. You know, so the capacitor, as its voltage increases, well, the inductor has to increase its voltage output until it runs out of juice. The moment it runs out of juice, then the capacitor can start throwing its energy back into the inductor. Okay, and so the cycle repeats. So, but in order for a little 100 nanofarad inductor to generate, you know, 10 amps of current, you know, which is what it naturally wants to do, is how much energy it has, you know, then it's got to be at a high voltage to do that, like 2 or 3 kilovolts. So that's why these can get, you know, dangerous and maybe even lethal if you get carried away with this. But it is a way of generating really high voltages, and I just showed you a taste of that, you know, with, you know, the, God damn it, stupid fucking, you know, I just showed you a taste of that with, you know, what I built here. So really quite simple, and, you know, but it gets the job done. So shit. But it gets the job done, you know, to demonstrate a principle. So, pretty cool. So, cheers. Just right there, I had to turn the video off.